Okay, hi everyone. My name is Nikolay. Welcome to my session on biologically plausible deep learning. So, did it change? Cool. Okay, so I work for IBM, but my session is purely based on my research interests. So whatever I say today is just my personal opinion and it has nothing to do with IBM. And with this out of the way, I just want to say that I'm also on Twitter. So if you want to connect with me, you can follow me on Twitter, message me on Twitter. I only tweet about data science and machine learning. So, I don't take photos of my Starbucks drinks and that kind of thing. So you'll be safe. This session is about neural networks. So of course, we'll have to start with the formal definition. Although I'm fairly certain that you all know what neural network is. If we go back and take a look at the definition given by Hiking, he basically says that the neural network is this massively parallel processor of interconnected units, and knowledge is acquired through a learning process, and it's stored in the synaptic weights. And every session on neural networks, of course, needs to feature this image from Wikipedia, otherwise it's not a legit session on neural network. In the top left corner, you see the neuron cell, and I have to tell you about, what the neuron cell is, and the dendrites around the nucleus and the axon and the presynaptic axon terminals and so on, and how it relates to the model of artificial neural network, which we have under. And this artificial neuron is just like a linear combiner that takes the inputs, sums them up, passes them through an activation function that adds some kind of nonlinearity like sigmoid, hyperbolic tangent, ReLUs, and so on, and then it passes it downstream. And then the idea of the deep learning is that we actually combine many of these artificial neurons together in separate layers, and all deep learning architectures have in common that they feature these cascades of hidden layers, and they learn different features. So the first layer will learn very basic features, the second layer will learn features based on the previous layer, and so on. And at the end, there will be something like a fully connected layer that makes predictions. So another common, let's say, feature of all deep networks is that they use backpropagation for learning, right? And deep neural networks have been very, very successful in specific challenges lately. Here is one example. This is the ImageNet large-scale visual recognition challenge. It's like a very large data set of images, something like 1.2 million images, and they're split. They are labeled in, I think, about 1,000 classes. And the challenge is to, label unseen data using a neural network or whatever. Here are two images, by the way, taken from ImageNet. And the idea is that because the classes are very fine-grained, for different dogs, you have the breed. So I wonder, if you look at these two images, first of all, how many of you can recognize the breed? Come on, play with me. Yeah, it's not that difficult. Husky, I heard it. Yeah, and I saw some hands being raised. Husky. Actually, these are two different breeds, right? One is a husky, the other one is an Eskimo dog. And I wasn't able to recognize them when I saw this. Probably most of you couldn't recognize that these are different breeds because you're not dog breeders. And it kind of tells you and shows you how difficult this challenge is, right? If a human needs an expert to be able to correctly label data, this is a very, very challenging task. And here you can see how different neural networks performed on this task over the years. In 2014, we have the Inception network, which is a convolutional neural network with fully connected layers at the end, that kind of lowered the error, the classification error, to 6.67%. Then, to 2015, we had another network that took it down to 3.57%, then another one in 2016 that took it down to 2.99%. Which is actually, by the way, better than what people can do. There was a paper, I think from Stanford, where they kind of put one of the PhD researchers in the room for 2 weeks, and he was just looking at images and labeling data, which is a very nice way of using PhD students' time. But he got something like 5.1%, I think. So these networks are already performing better than an average human. There is another example. That's the famous Deakin Network that plays Atari games. And here you can see this network is tested against the arcade learning environment, which features about 50 Atari 2600 games. And here, if you see the dotted line there, it kind of marks the threshold of at human or better level performance. So you can see that a deep network like DQN can perform really, really good, and in certain games it outperforms people. Games like pinball, games like Breakout, and so on. On the other hand, this network performs very badly on other games like Frostbite or Montezuma's Revenge. And what I was interested in was to answer the question why. Why people are good at some games, why machines in deep networks are better at others. And does this have to do with the biological plausibility of how these networks work? And if you think about biological plausibility, you have to break down the questions into 3 parts. First, is this how the human brain processes information? If we compare the human brain to a deep neural network, are they kind of processing information in the same way? The second question is this how people think? How similar is our thinking process to deep networks? And my third question is this how people learn? And probably I won't have the time to answer the third question or to address the third question, let's say, but let's focus on the first and the second question. So, is this how we think? Now, in artificial neural networks, we use backpropagation. That's how we encode the knowledge from the training data. And the backpropagation approach is, let's say, the workhorse of deep learning. And the way it works is that it kind of sends an error signal from the output layers down, or let's say up the upstream layers, all to the inputs, and then we adjust the synaptic weights to kind of better match the outputs to the actual data. And there is this credit assignment problem that kind of, it's hard to solve using conventional ways, because if you have to optimize the synaptic weights of one neuron, you need to know all the synaptic weights downstream to the output. Otherwise, you don't know how to adjust the weights to all the other neurons that this neuron sends signals to. And unfortunately, there is no evidence for an error signal in the neocortex. You know, in the human brain, information goes one way. If you think about the neuron cell, it always goes from the presynaptic neuron down the axon to the axon terminals that connect to the postsynaptic neuron. It doesn't go the other way. And even in 1986, when backpropagation was introduced in the original paper by Rumelhart, Hinton, and Williams, they say, you know, that's very unlikely. This algorithm is good, but you know, it's not a plausible model of how the human brain works. Surprisingly, there hasn't been much research in the area of getting rid of this flow, let's say, that it's not backpropagation is not biologically plausible. However, there is some interesting research being done. There was a paper by Lillikrab and collaborators published in 2014 that deals with this credit assignment problem, and they say, look, initially, because the neurons in the previous layer need to know all the ways downstream, what we have to do is sending an error signal. We also send information about the weights downstream, this W transpose matrix. But interestingly, if you, instead of sending the matrix of weights backwards, you just send this random matrix B here in green, it appears that with time, the network learns to use this random matrix to adjust the weights in the previous layer. So in a way, it appears that the network kind of learns to learn, right? So that's one approach. Later, they published another paper in 2017 using something called multi-compartment neurons. And the idea is, it's kind of borrowed by the idea of the how the pyramidal cells in the neocortex work, because they have like 2 groups of neurons. One penetrates different layers in the neurocortex, and then they connect to different areas of the brain. So they say, can we use the same in an artificial neural network? And what they do is they have like a neuron that has multiple compartments. And there is a dendrite connecting the outputs and feeding back the data to one of the compartments of the neuron, and then optimization happens locally. So there is some work being done in this area, and it's very promising, very interesting. The kickback algorithm is another approach that's not backpropagation per se. What they do there is they just kind of look at the error signals, and because the error signals are factorized to 2 components, a scalar at the output and this sum over all paths that represents the credit assignment problem, they say, well, we'll just use the scalar, and then we will look at the assignment locally and transform this into a local optimization problem. However, these approaches kind of work, and they perform well, but what I'm trying to say is that they're just the tip of the iceberg, because it's not just backpropagation. We have many other mechanisms in the human brain that we don't actually mimic in neural networks. Things like conductivity delays or stochastic binary values. You know, our brains don't operate on continuous variables and differentiable functions, unfortunately. We also require precisely timed cycles. You know, if you're doing backpropagation, you do forward pass, backward pass, forward pass, backward pass. And they have to be in a perfect synchronization, and that's not what happens in the human brain. So what I'm trying to say is that we are not there yet. Why does it matter? Because of this. This is one of the games where DQN performs horribly. It's called the Frostbite challenge. And if you're interested, by the way, you can Google it, and there are emulators that will let you play it in a browser. I thought I'll give it a try, like for 10 minutes, and that's what I've been doing for 2 hours at the airport, so be careful. It's very addictive. So the idea is that you're like an explorer on the Arctic or Atlantic. It has to be the Arctic, because at a certain point the polar bear comes and starts chasing you. So the idea is that as nightfall approaches, the temperature goes down, and you have to build an igloo to survive. And you have to jump on these floes in the river behind you and collect ice blocks that you use to build igloo. And then there are other agents in the game, like you know, these seagulls that try to harm you, and there are like fish and crabs and other animals and so on. And if you look at the performance of DQN compared to a human player, this is what you see. So for like 2 hours, a human player is capable of scoring something like over 4,000 points. The first initial version of DQN, the dotted line at the bottom, is the performance of the network over 924 hours, which is 168 hours in a week, so like 5 weeks' time, right? And for 5 weeks' time, initially, the score was marginally increasing. Then there were improvements on the architecture. We have something called DQN Plus and DQN Plus Plus, which kind of starts to approach the human player, but still, it takes like 5.5 weeks to get there. So why? That's the question that I'm interested in. And we know that the neural network doesn't actually operate as the human brain operates, but what about thinking? There's been this very interesting paper published by Lake in 2016, and they say that there are like 4 core components of human intelligence and human thinking process. They talk about intuitive physics, which I will talk about in details later on. The second component is intuitive psychology, which means our capability of recognizing that agents around us have their own internal motivations and goals, and they will act to fulfill these goals, right? So to give you an example, if I am on the North Pole and I see a polar bear approaching me, you know, I'm not going to stay stationary. You know, I am capable to realize that this agent has goals, and I'm one of these goals right now. And you know, if I want to preserve my life, I have to run away. For contrast, a deep network would have to experience like 1,000 deaths to realize that it has to run away from the bear, right? Now, the other component, causal models, has to do with our ability to, after we have recognized the agents and their motivations, to kind of simulate the situation in our head and make a prediction of what will happen. Now, here is me standing. There is the polar bear running towards me. The polar bear is hungry. It has internal motivations. What will happen if I stay here? Well, you know, 99% probability, if the bear doesn't die from a heart attack or something, it will eat me, right? So that's a prediction I can make. And the fourth component is called compositionality. And the idea is that we are very good at using simple and a finite number of building blocks to compose more complex systems. And there is this idea that actually by using combinations of a finite number of simple building blocks, you can produce an infinitely complex system. If you think about it from another perspective, you know the digits, 0 to 9, they're just 10 digits, but you can use them to produce infinite numbers, right? That's the same idea. So let me spend some time on intuitive physics. Now, the intuitive physics is our ability to understand the physical environment and make predictions on how events in this environment will unfold. I've done this experiment many, many times where I hold a ball in my hand and I ask people to come next to me, and I warn them that I will kind of release the ball like this without actually doing it, so that they can't actually see the ball falling down. They don't have this experience. And I say, I'll open my hand. Your goal is to catch the ball. And you can come as close as you want, and you can prepare your hands in a position that will maximize your chances. And I can assure you, all of them put their hand under the ball. No one tried to catch the ball here or here, right? But if you think about it, a neural network would start at random. It has to experience like 1,000 failures and slowly kind of reach the solution that the best strategy is to hold its hand under the ball. So why are we so good at this? There's been research showing that children at the age of 2 months kind of use intuitive physics. There is an ongoing debate, is this like an innate feature or acquired? I don't care, honestly. As long as we can use this in neural networks, I'm happy. There is this very interesting sentence from a paper that Battaglia published in 2013, saying that intuitive physics is like a cognitive mechanism similar to physics engines in computer games. So when you see this picture in the real world, or you see this situation and experience this situation, what your brain actually sees is something like this. This is my ball, and it has 2 forces acting on it. You have the tension force going this way, and then you have the Earth's acceleration times the mass going that way. And what your brain is doing, it's simulating this. And it says something like, okay, if this tension force disappears, what will happen with the ball? So where should I intercept the ball? There has been extensive research in people about intuitive physics. And actually, it's very interesting that this mechanism, although fascinating, is also very easy to fool. So there is this paper by Kulbrecht. And they run a series of experiments where they ask people to predict the trajectory of different objects. And here on top, you see this airplane, and the idea is that the airplane is flying horizontally, and then an object is being dropped off the airplane. And you'll be surprised how many people will predict the trajectory of this object to follow a straight line downwards, right? Part of the people will add a horizontal component, so they will predict a sloped line aligned with the direction of flight, but there is just a tiny fraction of people that will actually anticipate this curved line. And this happens because we don't have this experience. How many times have you dropped objects off an airplane? I haven't, That's why we make the mistake. Here is a second experiment where we have this curved tube, and there is a ball going through the tube, and you ask the people to draw the direction that the ball will follow after it leaves the tube. And most of them draw this curved circular path. They probably anticipate some kind of a centripetal force in this situation, because they don't, roll balls in curved tubes every day. Interestingly enough, if you change the situation, if you change the problem to a situation that people have experienced, then they perform better. Then you can't fool them. So if instead of this curved tube, you tell them that this is a garden hose, and they have to predict which way the water will flow out of the hose, no one will tell you that the water will go in a curved way, right? They will all say that it will spray straight forward, right? Which tells us something extremely important, that experience can override intuitive physics. So if we can combine intuitive physics with some learning from data, the predictions at the output should be very, very powerful. And this has been done, by the way. This is the Galileo Framework from 2015. And what the researchers did here is they kind of combined a physics engine plus a deep neural network. And the data that they feed to the neural network is like a movie. So you see these frames here on the left-hand side. You have a slope, and one object is traveling down the slope. And when it leaves the slope, it hits another object. So that's the data they feed to the system. And then the system recognizes the objects, and it uses an internal physics engine to do a simulation. And here in the middle, you can see the simulation going. And then based on the simulation, the system can make a prediction on which object is heavier and which object has higher friction coefficient. And that's a very difficult prediction to make, by the way, because that's not obvious. If I show you a ball and ask you to predict what the mass of the ball is, without seeing the ball in action, it's very difficult to answer this question. So back to Frostbite challenge. If we can actually add these components, like understanding of agents having their own motivations, intuitive physics, you don't have to jump 1,000 times in the water to anticipate that if you press the right button on the Atari 2600, you miss the next flow. If we can embed this knowledge and these mechanisms in our deep networks, then the expectation is that they will perform much, much better. Now there is this question on human learning, because DQN and most of our machine learning deep networks learn in a very, very different way than humans do. Can we improve something there? First of all, when I say very, very different way, deep networks typically run from labeled data, while the human learning process is mostly in an unsupervised setting. If you have a baby and the baby learns to recognize, balls and cubes, the baby does this in a natural way from the environment. You don't have to show your baby 1,000 images of balls and telling them, this is a ball, this is a cube, this is a ball, this is a cube, until the baby can recognize them, right? It happens naturally in an unsupervised way. That's not the case with deep networks. So that's one thing that we can improve. The other thing is knowledge transfer. If I solve one problem, I can kind of generalize and transfer this knowledge to a closer problem that I can also solve using the acquired knowledge. There was some work done by Parisotto. I think if you Google the paper, it's called Actor-Mimic Approach. And they kind of designed a network that plays the Atari 2600 challenge. But what the network does is it doesn't actually start to learn directly from the games. Initially, it observes a human player playing the games. So it learns looking at how humans play the games. And then you train it for a very short period of time. And then it appears that this network can actually perform better than DQN, which is quite fascinating. OK. Now, I am approaching the end of my presentation, so I have like 4 or 5 minutes left. And what I would like to address now is the question of, do we really care? OK, maybe deep networks are not learning in the same way as we do. Maybe they don't process information in the same way that we do. Nevertheless, they perform better than us at certain tasks like image recognition. There was a news, I saw it on Twitter today, that some neural network kind of beat the record on lip reading, and it performs now better than humans. There was another story from Microsoft Research, I think, where they have a network that can beat people on speech-to-text recognition, and so on and so on. So do we actually care? I would argue that we do care. And I could make the argument that we are measuring the success of these networks on a very limited set of problems that are very, very suitable for solving with neural networks and deep networks. However, even if I don't make this argument, I would like to point out that neuroscience has substantially influenced and informed artificial intelligence. If you think about, for example, experience replay, that's a key component of DQN. And the idea of experience replay is that The network plays a bit of the game, and then it stores this episode and goes over it again and again and again and again. Instead of playing, it just loops over it and tries to learn from what it has already done. And this is very similar to what we do in our brains using a mechanism called episodic memory. Quite often you make a decision in a situation and it's already done. But as times go by, you keep thinking about it and you go over it over and over again and you think, maybe I should have done something different. And you're trying to kind of learn from this experience. Use of working memory. Working memory, again, is a concept from neuroscience. And it has been utilized in recurrent neural networks and long-term memory networks, LSTMs, where we take a piece of data and we store it for an arbitrary amount of time, and then we can do computations over it. And there are many more mechanisms borrowed from neuroscience that are kind of slowly finding its way into neural networks, like efficient learning, imagination and planning, and so on and so on. There is this wonderful paper from DeepMind from 2017 called Neuroscience-Inspired Artificial Intelligence, and this paper gives you like a very, let's say, comprehensive list of how neuroscience has influenced deep networks, and also the other way around, how actually understanding coming from deep networks influenced neuroscience and the cognitive sciences. Okay, so this is my session essentially. I couldn't give you any answers. My goal was to kind of inspire you to think about neural networks in a broader, let's say, context, not just limited to, linear combiners and hyperbolic tangent and, stacking thousands of neurons together, but also to think about the mechanisms behind and the mechanisms that empower human knowledge and learning. So again, if you're interested in this, follow me on Twitter, message me on Twitter, come talk to me. I'll be probably at the IBM booth. In the meantime, if you have any questions, just, I'm happy to take them now. If I can see you. Okay, there is a question here at the front. Yeah, hang on, the microphone is coming.
You talk about those deep learning and reinforcement learning. What is your opinion on evolutionary approaches to solve those kind of problems?
What is my opinion on revolutionary approach?
Evolutionary.
Evolutionary? Yeah. Oh, I don't know. I'm not familiar with this concept because I don't look specifically at reinforcement learning. I look at neural networks. So probably not the best person to answer this question.
Okay, that's fine.
Yeah, thank you. Other questions? No? Okay, well then, thank you for your time. And again, I'll be at the IBM booth if you need me. Thank you.